4 light years. That's all that separates us from Alpha Centauri, the closest star system to our Sun. In cosmic terms, it's practically next door. But here's what's going to shift your perspective. When you actually look at what that distance means, when you work through the real numbers and the barriers they create, something quietly settles in. We are more isolated than most people ever stop to consider. Tonight, we're going to break down exactly what this system is, how we know how far away it is, and why that distance, just 4 light years, may be the most unconquerable barrier humanity has ever faced. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look toward Alpha Centauri in the southern sky, you see a single point of light. Bright, steady, unassuming. It looks like a star, but it is not a star. It is 3 stars, gravitationally bound to one another, orbiting a shared center of mass across a timescale that reduces all of human civilization to a momentary flicker. The first member is Alpha Centauri A. It is the largest and brightest of the 3, and in many ways the most familiar. Alpha Centauri A is close enough to our Sun that swapping one for the other would barely change life on Earth. It carries roughly 10% more mass than the Sun and burns about 1.5 times brighter. If it replaced our Sun tomorrow, Earth would be marginally warmer. The Sun would appear slightly larger in the sky. That is essentially the whole difference. Alpha Centauri A is not exotic. It is not extreme. It is, in the deepest sense, a near twin of the star we already know. The second member is Alpha Centauri B, smaller, dimmer, quieter. Alpha Centauri B carries about 90% of the Sun's mass and shines at roughly half the Sun's luminosity. If it replaced our Sun, Earth would grow colder. The light would be softer. A planet would need to orbit somewhat closer to receive comparable warmth. But Alpha Centauri B is still a stable, long-lived star fusing hydrogen into helium in its core. The same steady process our Sun has been running for 4.5 billion years. Nothing exotic here either. 2 ordinary stars, side by side in cosmic terms, each capable of supporting a solar system very much like ours. But here is where the system starts to behave in ways that feel genuinely strange. Alpha Centauri A and B orbit each other. Not in a clean circular path, in an ellipse, drawn out and oblong, so that their separation changes dramatically over time. At their closest approach, the 2 stars are about 11 astronomical units apart. That is roughly the distance from the Sun to Saturn. At their farthest, they pull apart to about 36 astronomical units, past the distance where Neptune traces its slow path around our own Sun. The orbital period is just under 80 years. They have completed 1 full orbit since the end of World War II. The next completion will arrive around 2037. Think about what that orbit looks like from the inside. If you were standing on a planet orbiting Alpha Centauri A, the second star would not be a distant point of light. At closest approach, Alpha Centauri B would blaze at roughly 1/100th the brightness of our Sun. That does not sound like much, but consider what it means in practice. It would be bright enough to cast shadows, bright enough to read by. A second sun in the sky, fainter than the first, but unmistakably a sun, not a planet, not a moon. A second star hanging there, warm and real and present. Every night would still be night, but the distinction between night and day would be softer, stranger, lit at the edges by something that had no equivalent in our own sky. The third member is different from both of them. Proxima Centauri is a red dwarf, a small, cool, dim ember of a star that represents the most common type of star in the galaxy. Though we rarely see red dwarfs in any list of the sky's bright objects because they are so faint. Proxima carries only about 12% of the Sun's mass. Its luminosity is roughly 17 hundredths of 1% of the sun's output. If it replaced our sun, Earth would freeze within hours. To orbit Proxima at a temperature where liquid water could exist on a planet's surface, you would need to be so close to the star that the planet's rotation would lock to its orbit, one face baking in permanent day, the other locked in permanent night, with a thin twilight ring at the boundary, the only place where temperatures might fall into a tolerable range. Proxima is the member technically closest to Earth. That is where its name comes from. Proxima. Nearest. It lives up to the name by a margin of just a few weeks of light travel time compared to the AB pair, and yet it does not orbit close to them. Proxima circles A and B at an enormous distance, roughly 13,000 astronomical units, which is approximately 2/10 of a light year, a fifth of the entire gap between the Alpha Centauri system and the Sun. At that distance, one orbit around the AB pair takes about 550,000 years. Over the billions of years this system has existed, Proxima has completed only a few thousand of those long, slow circuits. 3 radically different objects, bound together. One near twin of the Sun, one dimmer companion star, one dim red ember drifting at the edge. A system so varied it could serve as a sampler of the most common stellar types in the Milky Way. And this system is old. Between 5 and 6 billion years old, slightly older than the Sun itself. Alpha Centauri, A and B were already ancient when the cloud of gas and dust that became our solar system began to collapse. They were already ancient when the Sun ignited for the first time. They had been burning quietly, orbiting each other, cycling through their 80-year elliptical waltz for longer than Earth has existed. Put that against human history. All of recorded human civilization, every dynasty, every written language, every city ever built, spans roughly 6,000 years. Against the age of this system, that is less than 1/10,000th of 1%. The stars of Alpha Centauri did not notice us arrive. They will not notice when we are gone. The future extends just as far. In about 5 billion years, the Sun will exhaust the hydrogen in its core and expand into a red giant, consuming Mercury and Venus, and possibly Earth. But Alpha Centauri A and B will continue burning for billions of years beyond that point. And Proxima, that small dim ember, will outlast them all. Red dwarfs burn so slowly, with such miserly efficiency, that they will remain as faint glowing stars long after the larger stars have died. The universe itself will grow dark and cold before the last red dwarfs finally fade. Proxima Centauri will still be shining in a time so distant that the word future barely applies. The stars of this system were here before us. They will persist long after us. And understanding why the gap between us and them is so difficult to cross begins with understanding exactly how large 4 light years actually is. 4 light years is a distance that sounds almost manageable, a number, a measurement, something humanity has units for. But 25 trillion miles sits in a different category entirely. If you lined up every mile from Earth to the Moon, that journey covers roughly 250,000 miles. 25 trillion miles is 100 million of those Earth-to-Moon journeys, stacked end to end. That is the distance to Proxima Centauri. Alpha Centauri A and B sits slightly farther still, at about 437 light years, and nothing else is closer. In every direction across the entire surrounding volume of space, these 3 stars are the nearest neighbors our solar system has. The remarkable thing is how long humanity has known they were there. The object was visible for thousands of years to anyone living below the equator. Ancient observers in the southern hemisphere looked up and saw it. It was catalogued in the 2nd century, attributed to Ptolemy, recorded as part of the constellation Centaurus. Arab astronomers tracked it. Chinese astronomers observed it. For most of recorded history, people saw a single bright point of light hanging in the southern sky, steady and permanent, and assumed that was all it was. 1 star, 1 point. Nothing more complex than that. Here is what no one suspected for all those centuries. It was not one star, it was two. In 1689, a Jesuit priest named Jean Richaud was observing from Puducherry in India when he turned his telescope on the object and saw something unexpected. The point of light separated. Not into a blur, not into an artifact of the lens. Into two distinct stars, orbiting each other. A gravitationally bound pair sharing the same region of space. Circling a common center in a slow, measured ellipse. Double stars were rare discoveries. Most stars, through a telescope, appear single. Finding two stars genuinely bound to each other was scientifically significant. It meant you could study orbital mechanics. It meant you could watch two massive objects pull on each other across decades and learn something about the forces involved. Richaud's observation, made from a colonial outpost on the coast of India, was the first moment any human being understood that Alpha Centauri was not what it appeared. But here is where it gets strange. Knowing something is a double star and knowing how far away it is are completely different problems. And for the next century and a half, astronomers tracked the pair without knowing either of those two things completely. By the early 1800s, patient observers had built up decades of positional measurements. They had established the orbital period, just under 80 years. They had calculated the orbital eccentricity, the degree to which the ellipse stretches and squeezes compared to a perfect circle. They could predict where each star would appear relative to the other at any point in the orbit. The geometry of the system, measured in angles and arc seconds, was increasingly well understood. But the absolute distance, the actual gulf in miles or light years between Earth and those two stars, remained unknown. Angles alone cannot tell you that. To get a real distance, you needed a different technique entirely. You needed parallax. In 1832, Thomas Henderson arrived in Cape Town, South Africa, to take charge of the Royal Observatory there. He was a Scottish astronomer, precise and methodical, and he brought with him a specific purpose. He wanted to measure the parallax of Alpha Centauri. Parallax is the apparent shift in a star's position as Earth moves around the Sun. Hold a finger up close to your face and close one eye, then the other. Your finger appears to jump against the background. The closer the finger, the bigger the jump. Stars work the same way. As Earth orbits the Sun, a nearby star should appear to shift slightly against the more distant background stars. Measure that shift, measure the baseline Earth travels, and you can calculate the true distance. The challenge is the scale of the shift. For even the nearest stars, the apparent wobble is smaller than 1 arcsecond. An arcsecond is 1/3600th of a single degree. To put that in concrete terms, a coin held at arm's length spans roughly 1/800 arcseconds across its face. Henderson was searching for a shift smaller than 1 arcsecond, smaller than 1/1800th of that coin's width. He was hunting for a motion that barely existed on the scale of any instrument available to him, and yet he found it. He observed for months. He made hundreds of measurements. He tracked Alpha Centauri against the fainter background stars, noting its position night after night, season after season, watching for the tiny rhythm of the parallax shift as Earth swung across its orbit. The wobble was there. Small, almost impossibly small, but there. Henderson had, in his data, the first measurement of the true distance to another star. Then he did nothing with it. He worried about instrument error. He worried about atmospheric distortion. He was cautious, methodical, careful, almost to the point of paralysis, and he held his data for years, unwilling to publish results he could not be fully certain were clean. It was a human failure dressed as scientific rigor. Meanwhile, in 1838, Friedrich Bessel in Germany published a measurement, not of Alpha Centauri, of a different star, 61 Cygni. Bessel had applied careful mathematical techniques to isolate real signal from measurement noise, and he published his parallax result with full error accounting. His result was confirmed. He became the first person in history to publish a verified stellar distance. The achievement of measuring the true scale of the universe for the first time went to Friedrich Bessel, and it went to him because Thomas Henderson had the result first and waited too long. Henderson published his Alpha Centauri measurements in 1839, 1 year after Bessel. The result was still his. The data was still real, but the credit for the breakthrough belonged elsewhere. His number was 4.3 light years. Modern instruments place Proxima at 4.24 light years and Alpha Centauri A and B at 437 light years. Henderson, using telescopes made of metal and glass in the 1830s, with no electronics, no computers, no space-based observatories, landed within a few percent of the modern value. The measurement was accurate. The hesitation was the only thing that cost him. What those numbers meant, once both Bessel and Henderson had established them, was genuinely staggering, not roughly far away, not somewhere on the outer edge of our local neighborhood. 25 trillion miles for the nearest one. The stars were not lanterns hung above the Earth. They were distant suns scattered across incomprehensible gulfs of empty space, each one a separate solar system in waiting, each one separated from the next by distances that made the entire span of human history feel like a single heartbeat. The first confirmed measurement of that distance was published in 1839, nearly 200 years ago. And in the time since, humanity has not crossed it, has not sent a probe there, has not transmitted a signal that has completed the journey. The gap is just as wide today as it was when Henderson folded up his observational logs in Cape Town and posted his results to London. And understanding why that gap has proven so resistant to crossing requires looking closely at what that distance actually means when you try to move through it. That distance is not just a number on a chart. It is a physical fact with consequences, and those consequences run deeper than most people expect. Start with what humanity already knows. From 25 trillion miles away, using nothing but light, scientists have measured the mass of each star in the Alpha Centauri system. They have analyzed the composition of those stars, their surface temperatures, their ages. They have identified a planet orbiting Proxima Centauri and mapped out where liquid water could theoretically exist on its surface. They have modeled how the gravitational pulls of 3 stars interact, and whether the orbits of any potential worlds would remain stable over millions of years. All of that knowledge arrived here as photons, as light that left the system years ago and eventually fell into telescopes pointed at the southern sky. Humanity has mapped the system in remarkable detail, and humanity has never touched it, has never sampled it, has never come close. That is the first thing the distance means. Here is the second. Light travels at approximately 186,000 miles per second. That is not a record waiting to be broken by better engineering or a future breakthrough in propulsion. It is not the current top speed of a technology that is still developing. It is a fundamental law of physics, an absolute ceiling. Nothing in the universe carries information or matter faster than that. The limit is baked into the structure of space itself, which means that when you look at Alpha Centauri in the night sky, you are not seeing it as it is. You are seeing light that left the system 4.24 years ago. The star you're looking at is the star as it was in the past. If something happened to Proxima Centauri today, a flare, a catastrophic event, anything at all, that information could not reach Earth for 4.24 years. There is no faster channel. There is no shortcut. The separation between this solar system and the next one is not just a gap of distance. It is a gap of time. And that gap compounds the farther out you look. Sirius, one of the brightest stars visible from Earth, sits about 8.6 light years away. The light arriving from it left during a different decade. Epsilon Eridani, at about 10.5 light years, sends light that is over a decade old by the time it reaches a telescope. Tau Ceti, roughly 12 light years out, is farther still. Alpha Centauri, at 424 light years, is the closest neighbor in any direction. If the galaxy were a city, it would be the house next door. But next door in this city means a walk of 424 years at the speed of light. And nothing moves at the speed of light. The answer was stranger than expected. The fastest spacecraft humanity has ever built moves at a speed that sounds extraordinary. The Parker Solar Probe, launched in 2018, reaches approximately 120 miles per second during its closest passes near the Sun. That works out to roughly 430,000 miles per hour. At that speed, the probe could circle the entire circumference of Earth in about 3.5 minutes. It could reach the Moon in roughly 33 minutes. These are not vague impressions of speed. These are precise numbers, and they describe something moving faster than any object humans have ever created. But the distance to Alpha Centauri is not a moon problem. It is not even a solar system problem. At 430,000 miles per hour, the Parker Solar Probe would take approximately 6,700 years to reach Proxima Centauri. Not decades, not centuries, 6,700 years. The probe launched in 2018. If it had been aimed at Alpha Centauri instead of the Sun, the calculated arrival year would be somewhere around 8718. Every civilization currently on Earth would be unrecognizable or gone. Written language as it exists today would be a historical artifact. The 6,700 years separating launch from arrival is longer than the entire span of recorded human history. Not almost as long, longer. The Voyager probes are actually leaving the solar system. They travel at approximately 38,000 miles per hour, fast enough to have carried them beyond the reach of the Sun's dominant influence. At that speed, a Voyager-class probe aimed at Alpha Centauri would take roughly 75,000 years to arrive. New Horizons, the spacecraft that passed Pluto in 2015, moves at about 36,000 miles per hour, and would need somewhere between 70,000 and 80,000 years to make the same journey. Think about what 75,000 years means. That is approximately when modern humans were beginning to spread out of Africa. Hunter-gatherers with stone tools, fire, and almost certainly language, but nothing else. No agriculture, no permanent settlements, no cities, no writing, no wheel, every war ever fought, every empire ever built, every language ever spoken, every invention from the plow to the microprocessor, all of it fits inside the travel time of a Voyager speed trip to the nearest star. And even those timescales assume the spacecraft survives. They do not. Electronics fail over decades, not millennia. Power sources run out. Structure degrades under constant bombardment from micrometeorites and cosmic radiation. The Voyager probes are already operating on systems that engineers describe as fragile, held together by workarounds and careful management. And they have been traveling for less than 50 years. A journey measured in tens of thousands of years would reduce any current spacecraft to dead, inert junk long before it crossed even a fraction of the distance. The machinery would stop working. The signals would go silent. The probe would continue drifting, but blind, powerless, and effectively gone. So the situation is this. The nearest star system is 4.24 light-years away. The fastest thing humanity has ever built would take 6,700 years to reach it. Craft actually leaving the solar system would take 75,000 years. None of them could survive the journey. And the speed of light, which would reduce that trip to 4.24 years, is not a ceiling that technology can one day pierce. It is the law. What that means is that crossing this distance requires something entirely different from anything currently flying. Not faster in the way the Parker Solar Probe is faster than Voyager. Faster by an order of magnitude that changes the nature of the problem entirely. And that is exactly what the next question is about. So let's see what happens as we go faster. At 1% of the speed of light, the trip to Alpha Centauri takes 424 years. That number needs a moment to settle. 1% sounds modest, 1/100th of the ultimate speed. But 1% of the speed of light is roughly 1.86 million miles per hour. The fastest spacecraft humanity has ever built reaches about 430,000 miles per hour. To hit 1%, you would need to go more than 140 times faster than that. Not incrementally faster, not a generation of improvement faster, 140 times faster. And even then, the trip takes 424 years. That is longer than the entire history of the United States. Longer than the existence of most nation-states in their current form. A civilization that launched a ship at 1% of light speed today would be watching the ship arrive in the year 2449. Whatever country funded the mission would almost certainly be unrecognizable by then. The only plausible vessel for a journey like that is what engineers and theorists call a generation ship. A closed, self-sustaining habitat. Not a spacecraft in any conventional sense. A world. Thousands of people living, working, and dying aboard it over centuries. The crew that departs never arrives. Their children inherit the mission. Their grandchildren inherit it again. The people who finally set foot on another world will have been born in space, raised in space, and will have known nothing else. They will arrive at a destination chosen by ancestors they never met, on a mission they did not volunteer for. And that raises a question that has no clean answer. Is it right to commit unborn generations to a journey they did not choose? Children born aboard that ship never had the option to refuse. They will never stand on a planet, breathe unfiltered air, or see a natural sky. If the ship fails halfway, they die in the void between stars. If the destination proves uninhabitable, they have nowhere to go back to. There is no abort. There is no return. There is also no real communication. Radio waves travel at the speed of light. A message sent from the ship takes 4.24 years to reach Earth. A reply takes another 424 years to return. An 8.5-year round trip for a single exchange. A child born on the ship could grow old before hearing a response to a question asked in youth. After a few generations, the cultural gulf between ship and Earth would be so vast that shared language and shared assumptions might dissolve entirely. The ship and the civilization that launched it would be strangers. The picture did not hold. Push the speed up and the picture begins to change. At 10% of light speed, roughly 18.6 million miles per hour, the trip drops to 42.4 years. That is within a single human life. Board the ship as a young adult. Arrive in your 60s. A long career, a demanding one, but a single lifetime, beginning to end. The mission becomes something one person can hold in their own hands. At 20% of light speed, roughly 37 million miles per hour, the trip takes 21.2 years. Board in your 20s, arrive in your 40s, still young enough to do serious work at the destination. Suddenly the journey starts to feel almost achievable, not easy, not near, but possible in human terms, in ways the 424-year version is not. And then the other side of the picture arrives. At 20% of light speed, by the time you arrive, you have been out of real-time contact for more than 2 decades. The last message you received from Earth is already 4 years old the moment you land. Everything you knew of home is at minimum 25 years stale. The mission planners who briefed you may be retired or gone. The governments that funded the mission may have changed hands, collapsed, or simply moved on. Earth, indifferent to a ship that left a generation ago, may no longer be watching. And there is one more thing. In those 21 years, the technology on Earth did not stand still. A later mission, launched years after yours with a faster drive, might overtake you in transit. You could arrive to find that someone else got there first. Your mission, the one you gave decades of your life to, superseded before it finished. Not celebrated, not even particularly noticed. That is the cost of speed at the levels we can almost imagine. But the physical costs are more immediate than the human ones, and they arrive first. Because interstellar space is not empty. Not in the way it appears from here. The region between stars holds thin gas and dust, approximately 1 atom per cubic centimeter on average. At the speeds we are talking about, that matters enormously. At 10% of light speed, every particle the ship encounters, no matter how small, carries extraordinary energy. Think about a paperclip. A single paperclip, roughly 1 gram of metal. At 10% of light speed, If that paperclip mass of material were to strike the ship, the energy released would equal approximately 43 tons of TNT, roughly 3 times the energy of the Hiroshima bomb, from a single gram. At 20% of light speed, that same gram releases approximately 170 tons of TNT, 13 times Hiroshima, not from an asteroid, not from a boulder, from a paperclip, from a grain of sand. The interstellar medium does not consist of paperclips. It consists of atoms and microscopic dust particles, but there are a great many of them, and at these speeds, even single atom impacts transfer momentum, creating small but accumulating drag that slows the ship and demands extra propellant to compensate. And the occasional larger particle, even a few microns across, becomes a potential catastrophe. Proposed defenses exist. A massive dense forward shield could absorb the impacts, but a denser shield means more mass, and more mass makes acceleration harder. Magnetic fields could deflect charged particles, but they do nothing against neutral debris. Multiple redundant layers could improve the odds, but none of these solutions are clean, and a single piece of unlucky debris at the wrong moment could end the mission entirely. There is no redundancy for that. Which brings us to the fuel problem, and this is where the mathematics turn genuinely unforgiving. Every kilogram of payload requires propellant to accelerate it. But the propellant itself has mass, and that mass also needs to be accelerated, which requires more propellant, which also has mass, which requires more propellant still. The requirement scales exponentially. This is the rocket equation, and it has no mercy. Current chemical rockets achieve roughly 1% of their total launch mass as useful payload, 99 kilograms of fuel for every kilogram of spacecraft. For an interstellar mission at 10 or 20% of light speed, the ratios become essentially impossible. Thousands or millions of times the payload mass in propellant, before accounting for the deceleration burn needed to actually stop at the destination. Exotic alternatives have been proposed, and each one runs into a wall. Nuclear pulse propulsion would detonate small nuclear devices behind the ship, using the blast pressure to accelerate. The physics work in principle, but nuclear weapons in space are blocked by international treaties, and a ship detonating thousands of bombs per second raises questions no treaty framework currently addresses. Fusion rockets would fuse hydrogen into helium, extracting enormous energy as thrust. The problem is that controlled sustained fusion has not been achieved even in stationary Earth reactors, after decades of trying. Building a compact fusion drive for a spacecraft before that problem is solved is a distant prospect. Antimatter drives would annihilate matter against antimatter in a perfect conversion of mass to energy. The energy output would be extraordinary. The supply would not. Humanity currently produces antimatter in nanogram quantities per year, at enormous cost. An interstellar mission would require kilograms or tons. Producing that much antimatter at current rates would take millions of years and consume more energy than human civilization has generated across all of recorded history. Laser light sails would avoid the fuel problem entirely. A massive array of lasers, based on Earth or in orbit, would push a reflective sail without any onboard propellant. The ship would carry almost no mass. It could accelerate to significant fractions of light speed. This concept is the basis of serious research proposals, and it may be the most physically credible approach we currently have, but it has one fundamental problem. Once the sail leaves, the lasers stay behind. There is no way to slow down. The craft would flash through the Alpha Centauri system at a substantial fraction of light speed, passing through in hours with no ability to stop, orbit, or land. Every method hits a wall, not a wall of insufficient technology, not a wall that better engineering might one day breach, a wall of physical law. The speed of light cannot be exceeded. Momentum must be conserved. Energy cannot come from nothing. These are not engineering problems awaiting a clever solution. They are the structure of the universe. The hazards that get worse with speed are not the biggest obstacle. They are the consequences of the real obstacle, which is that no method of propulsion currently proposed can both get a ship to Alpha Centauri in a human lifetime and stop it when it arrives. And that problem runs deeper than any of the individual barriers described here. Suppose the ship does fly. Suppose every propulsion problem is solved, every physical wall somehow bypassed, every engineering obstacle cleared. The ship exists. It launches. It accelerates. Now ask a different question. What does that journey do to the people inside it? The first thing it does is irradiate them. Space is not a benign emptiness. It is saturated with cosmic rays, high-energy particles, mostly protons, accelerated to near light speed by supernovae and other violent events scattered across the galaxy. They travel in every direction. They penetrate matter. In biological tissue, they break DNA strands, cause mutations, and raise the risk of cancer. On Earth, the planet's magnetic field and atmosphere absorb most of this bombardment before it reaches a person standing at the surface. The average person on Earth receives roughly 2 to 3 millisieverts of radiation per year. A millisievert is a unit of absorbed radiation dose, a measure of the energy deposited in tissue. Astronauts on the International Space Station receive roughly 50 to 200 millisieverts per year. That is 50 to 100 times the ground level rate. And the ISS is still inside Earth's magnetosphere. It is still shielded. Astronauts spend months there, not years. On an interstellar voyage, there is no magnetosphere. There is no planet shielding the crew from one side. There is no hole thick enough to stop everything coming in from every direction at once. Over 20 years, the accumulated dose reaches hundreds to thousands of millisieverts. That is not a manageable inconvenience. That is a serious, sustained biological threat. There are approaches to shielding. Water absorbs high-energy particles effectively because hydrogen atoms are good at stopping protons. Some spacecraft designs surround the crew compartment with water tanks that serve double duty, shielding the crew while also serving as storage. But water is heavy. Every kilogram of shielding competes with every kilogram of fuel and payload. Magnetic shielding can deflect charged particles the way Earth's own field does, but it requires continuous power, superconducting magnets kept at cryogenic temperatures, and still cannot stop neutral particles. Things like neutrons, which pass straight through a magnetic field and require physical mass to absorb. Every approach trades one problem for another. More protection means more mass. More mass means more fuel. More fuel means the journey may never launch at all. There is no solution that closes the problem cleanly. But something was wrong. Even if the radiation problem were solved perfectly, the crew would still be facing something no isolation study has ever measured at this scale. 20 years in a confined space. The same corridors, the same rooms, the same people. Earth receding behind them to a point indistinguishable from any other star. Alpha Centauri brightening ahead so slowly that no human eye could detect it changing from week to week. Even at 20% of light speed, the view barely changes from one year to the next. The stars are so distant that motion through interstellar space produces no landmarks, no sense of progress, no passing scenery. Nothing outside the windows moves in any perceptible way. Humans evolve for variety, for seasons, for horizons, for the ability to walk somewhere new. The longest Earth-based isolation studies, experiments simulating long-duration space missions in confined habitats, last months, occasionally a year or two. They already show rising depression, interpersonal conflict, and declining motivation. We have no data on 2 decades. No one does. What a human mind does after 10 years in a box with the same 8 people, no outside authority, no courts, no police, no possibility of outside intervention, is genuinely unknown. The crew would have to build its own governance, its own conflict resolution, its own social norms and enforcement. A self-contained micro-society, sealed, alone, drifting. And as the years pass, a second problem would emerge. The connection to Earth would begin to dissolve. In the first year at 10% of light speed, the ship is about 600 billion miles out, roughly a tenth of a light year. A message takes about 5 weeks each way. A round-trip exchange takes about 10 weeks, slow but workable, something like correspondence. After 10 years, the ship is roughly 1 light year out. Messages take 1 year each way. The round trip is 2 years. Any answer to a question arrives 2 years after the question was asked. Earth's news, when it arrives, is always a year stale. After 20 years, the ship is about 2 light years from Earth. Farther from home than Proxima Centauri is from our solar system, the round trip for a single exchange is 4 years. Earth cannot help with any problem that unfolds in real time aboard the ship. By the time advice arrives, the situation that prompted the question has long since resolved or ended in disaster. After 50 years, the ship is roughly halfway. The original mission planners are old or gone. The generation that built the ship may be dead. People on Earth who were children at launch are now middle-aged, and the mission is ancient history to them, a thing from their grandparents' era. The crew's transmissions home are dutiful status reports from a mission most people on Earth have stopped thinking about, and the round-trip delay is now over 4 years, roughly equal to the entire distance between Earth and Alpha Centauri. After a century on arrival, Earth is 4.24 light-years behind. The crew sends the arrival message. It takes 4.24 years to reach Earth. Earth's congratulations takes another 4.24 years to come back. By the time the response arrives, the crew has been at Alpha Centauri for over 4 years already. They have explored the system. They have made decisions. They have perhaps begun building something. Earth's response addresses news nearly a decade old. And there is something deeper happening beneath that delay. Children born aboard the ship during the voyage have never seen Earth. It exists for them only as stories. Grandchildren born at Alpha Centauri will grow up on a different world, under different stars, with no lived memory of anything their ancestors left behind. Earth becomes mythology to them, an unreachable ancestral homeland. These people are genetically human, but they are culturally, linguistically, and socially something else. Alpha Centaurans, a new branch of the species, drifting apart from the origin, unable to return. This is the reframe that rarely gets made. Interstellar colonization is not expansion, not in the way the word usually implies. Even Earth's most remote settlements remain connected to the whole. A person in the deepest Amazon can, in principle, travel to Tokyo within a lifetime. They can send a message and receive a reply the same day. Alpha Centauri permits none of that. No return, no meaningful real-time connection. Not disconnection by hardship, but disconnection by physics, permanent and absolute. A step humanity has never taken, toward a future it cannot fully imagine. Whether that fragmentation is a tragedy or the natural and inevitable way a species spreads across a galaxy is a question left genuinely open. But the distance itself creates one more complication, one that does not get discussed as often as the propulsion or the radiation or the psychology. The target is moving. Everything in the galaxy orbits the galactic center. The sun moves at roughly 140 miles per second around the Milky Way's core. Alpha Centauri has its own orbital velocity. And Alpha Centauri's radial velocity, the component of its motion directly toward or away from us, is roughly 3.8 miles per second toward the sun, which means the two systems are closing at about 13.8 miles per second. In about 27,000 years, Alpha Centauri will reach its closest approach to the solar system, roughly 3.2 light-years away, and then begin pulling back. In about 33,000 years, it will be farther from us than it is today. A mission cannot aim at where Alpha Centauri is now. It must aim at where Alpha Centauri will be when the ship arrives, decades or centuries later, accounting for the motion of the sun, the motion of the target, and the gravitational influences encountered along the way. The image is a quarterback throwing not to where a receiver is standing, but to where the receiver will be when the ball gets there. The ball, in this case, traveling for decades. the receiver crossing a very large field very slowly. A 1-degree error in the initial trajectory, compounded over 4.24 light years, misses the target by trillions of miles. Not a near miss, not close enough to correct. Stranded in empty space with no destination and no way back. Wait, none of humanity's outbound spacecraft are even aimed in that direction. Humanity has sent exactly 5 spacecraft on trajectories that will eventually escape the solar system entirely. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, New Horizons. Not one of them is headed toward Alpha Centauri. Voyager 1 is currently the farthest human-made object from Earth, roughly 15.8 billion miles out, about 159 times the distance from Earth to the Sun. In August 2012, it crossed the heliopause, the boundary where the solar wind fades and the interstellar medium begins. It is, by that definition, in interstellar space. It is traveling at about 38,000 miles per hour. And it is heading toward the constellation Ophiuchus, nowhere near Alpha Centauri. In about 40,000 years, it will pass within roughly 1.6 light years of a star, called Gliese 445, without stopping, without slowing, without anything aboard still functioning. The voyages are about 20 light hours from Earth. That is approximately 0.0223 light years. Alpha Centauri is 4.24 light years away. Alpha Centauri is roughly 1,843 times farther than the farthest thing humanity has ever sent into space. We have dispatched robots to the edge of our own yard. The next star over remains entirely unreached, unapproached, and, with current trajectories, unintended. The distance is not only a physics problem, it is not only a propulsion problem or a shielding problem or a psychological problem. It is all of those problems at once, layered on top of each other, each one severe enough to stop a mission on its own, and none of them are close to being solved. So lift your eyes from that yard, look all the way out to the destination itself, because the destination is real, the planets are real, the mission proposals are real, and what humanity has actually imagined, designed, and funded deserves a full hearing before the reckoning arrives. Start with silence. Humanity has been listening for decades. The search for extraterrestrial intelligence has pointed radio telescopes at the sky, including the direction of Alpha Centauri, scanning for any signal that might indicate something out there is broadcasting. So far, nothing. Not a whisper. Not an anomaly that survives scrutiny. And that silence has its own weight. A radio message sent to Alpha Centauri today would take 4.24 years to arrive. Any reply would take another 4.24 years to return. A single exchange would span 8.48 years. You would send a question as a child and receive the answer in high school, and that assumes something is there to answer. Either humanity is genuinely alone in its local neighborhood, or anything living out there is not broadcasting in ways humanity recognizes. Either way, the sky has offered nothing, but the planets are there. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet orbiting the nearest star to Earth. It is about 1.3 times Earth's mass. It completes one orbit every 11.2 days. Because Proxima is a dim red dwarf, its habitable zone, the band of distance where liquid surface water could exist, sits very close to the star. Proxima b orbits at roughly 4.7 million miles out. That is about 5% of the distance between Earth and the Sun. At that distance, the planet is almost certainly tidally locked. One hemisphere faces the star permanently. The other faces permanent darkness, scorched on one side, frozen on the other, howling winds racing around the boundary, trying to equalize the temperature. But here is where it gets strange. Proxima is not a quiet star. It is an active flare star, erupting in sudden bursts of radiation that can strip a planet's atmosphere over millions of years. Whether Proxima b has an atmosphere at all, whether it has a magnetic field strong enough to deflect that radiation, whether it has liquid water anywhere, is genuinely unknown. The planet was detected by measuring the tiny wobble it induces in its star's motion. There are no images. There are no spectra of its surface or air. It could be a world with oceans and chemistry. It could be a barren, irradiated rock. No one knows. In 2022, a second planet was confirmed. Proxima Centauri C orbits even closer, at about 2.5 million miles from its star, and is smaller, roughly a quarter of Earth's mass. Too close, probably too hot, almost certainly not hospitable. Alpha Centauri A and B may also have planets. None have been confirmed. The detection methods available from Earth favor large planets close to their stars. Smaller, more distant worlds, the kind that might interest a colonist, could be orbiting A or B right now and humanity would not know it. Real mission proposals exist. They are serious, named, and funded. And each one, examined closely, runs into a wall. Breakthrough Starshot was announced in 2016, backed by investor Yuri Milner and supported publicly by Stephen Hawking. The concept is elegant. Build thousands of tiny spacecraft, each the mass of a gram, mounted on a sail roughly a meter across and only a few atoms thick. Aim a combined laser array at roughly 100 gigawatts of power at the sails. Accelerate them to 20% of the speed of light in minutes. Shut off the lasers. Let them coast. They reach Alpha Centauri in about 20 years. Data transmits back across 4.24 light years. Total mission time, roughly 25 years, within a human generation. The hurdles are extraordinary. The laser array alone would cost billions to tens of billions of dollars, and would likely need to be built in space, because the atmosphere distorts and absorbs light at that scale. The sail must be near perfectly reflective. At 100 gigawatts, even tiny absorption at the material level converts to enough heat to vaporize the craft instantly. Current materials are nowhere close. The chip itself must carry a camera, sensors, a computer, a power source, and a transmitter in a package that weighs about as much as a paperclip. That exceeds current miniaturization by orders of magnitude. Once coasting, any course correction is impossible. And at 20% of the speed of light, even a grain of dust in the interstellar medium carries catastrophic impact energy. The plan is to launch thousands of them and accept that most will fail. A shotgun approach. Quantity compensating for fragility, and even if 10% survive, the result is a fast flyby. Hours at Alpha Centauri, no orbit, no landing, no sustained presence. Project Daedalus came earlier. In the 1970s, a team at the British Interplanetary Society designed a fusion-powered craft intended to reach a nearby star. Daedalus would burn helium-3 and deuterium, igniting fuel pellets 250 times per second by electron beams, propelling the craft to 12% of the speed of light. The total mass was about 54,000 tons. The payload, the part that actually arrives, was roughly 450 tons. Less than 1% of the total mass. A 36-year trip. A fly-through, not a stop. The problem is the sustained fusion has not been achieved usefully on Earth, not even today, and the helium-3 required barely exists here. It would have to be mined from the moon or skimmed from the upper atmosphere of Jupiter. An entire space infrastructure would need to exist before a single Daedalus could launch. Project Icarus, designed in the 2010s as a successor, refined the engineering but faced every identical barrier. Different numbers, same walls, and then there are generation ships, not spacecraft in any conventional sense, worlds, massive rotating habitats with artificial gravity, closed-loop air and water, agriculture, manufacturing, hospitals, governance structures, and communities of thousands. Self-sufficient for centuries, with no resupply and no rescue. The physics of a multi-century voyage demands it. The engineering is plausible in principle, the human problem is something else entirely. Later generations, born in space, would inherit a mission they did not choose. They would have no memory of Earth and no ability to return. They could refuse. They could fracture along political or religious lines, trapped together in an inescapable vessel with nowhere to go. And on arrival, roughly 4 centuries after departure, the civilization that launched them would be long gone. The colonists would be committed permanently. Succeed at Alpha Centauri or go extinct. Now consider what a successful mission would actually return. A probe reaching the Alpha Centauri system could observe the 3 stars at close range, map their surfaces, study their stellar winds and magnetic fields in ways impossible from 25 trillion miles away. Directly comparing A and B to the Sun would refine the models that describe how stars age. And Proxima, the nearest red dwarf, would offer something more specific. Red dwarfs make up roughly 70% of all stars in the galaxy. They are dim and difficult to study at a distance, but they are extraordinarily long-lived. Long after the Sun exhausts its fuel and the galaxy dims, red dwarfs will still be burning. Understanding them is understanding the far future of the cosmos. A probe could image Proxima b directly, analyze whatever atmosphere it has, search for oxygen, methane, complex organic molecules, the signatures of life. Finding even simple microbial chemistry there would be the most transformative discovery in the history of science. Not just interesting, not just significant. If life arose twice in the same handful of light years, then the universe is full of it. Humanity would not be a strange, lone accident. It would be part of something vastly larger. The cost of even a small probe runs to billions, possibly tens of billions of dollars. The result would take decades to arrive. Proxima b might prove hospitable, it might prove barren. Whether that uncertainty justifies the investment is a genuine question. Different people will answer differently. There is no single correct answer. That is not a weakness of the science, it is the nature of a value judgment. If the nearest star is this hard to reach, the math compounds in one direction only. Sirius sits at 8.6 light years, Vega at 25, the Pleiades at 440, the center of the Milky Way at 26,000, the Andromeda Galaxy at 2.5 million. Beyond some distance, travel in any meaningful sense does not simply become difficult. It becomes effectively impossible, not for lack of ambition. The speed of light cannot be changed. Space cannot be compressed. The 25 trillion miles cannot be wished away. The farthest any human being has ever traveled is the Moon. About 240,000 miles, roughly 1.3 light seconds, a 3-day trip. Alpha Centauri is approximately 128 million times farther than the Moon. Humanity has not left home. Not really. Not yet. And this may not be a problem with an answer. If no civilization can travel between stars, then every civilization that has ever existed or ever will exist lives and dies alone, makes contact with nothing, reaches nothing beyond its own solar system. Distance itself, not hostile aliens, not self-destruction, not missing technology, may be the filter that keeps the universe silent. That silence humanity has been listening into for decades may simply be the sound of physics doing exactly what it does. There is a word for what humanity is, seen from this angle: castaways. On a tiny island, surrounded by an ocean too vast to cross, looking out at distant shores it can see, but never reach. But here is the other side of that thought. The universe is not indifferent to humanity because it is cruel. It is indifferent because it is vast beyond the scale of human plans. Learning that the Earth was not the center of creation was once experienced as a humiliation. It turned out to be a liberation. It gave humanity perspective, understanding that the Sun is one star among hundreds of billions, and that those stars are separated by gulfs that may never be crossed, does not diminish what humanity is. It contextualizes it. Think about what has actually been accomplished from this tiny island. The mass of a planet orbiting a star 25 trillion miles away, measured using nothing but mathematics and the motion of light. The composition of stars known before any human left the atmosphere. The age of the universe, the shape of galaxies, the expansion of space, all of it worked out by small groups of people on a rocky planet with pencils and telescopes and patient thought. Consciousness doing what the rest of the universe, as far as anyone knows, cannot do. Comprehending itself, asking questions, following them wherever they lead. Humanity should keep trying, keep developing propulsion, keep designing missions, keep listening and searching for anything in the sky that replies. Some barriers may yield, some may not. Sometimes the universe says no, and when it does, the honest response is not despair, but acceptance, and then gratitude for the one home that is known, the one world confirmed to carry life and consciousness, and the capacity to wonder at a universe that gave rise to something capable of wondering at it at all. That may be all humanity ever has. It is not nothing.